Okay. Yeah. Yes, good morning, dear students. Welcome to the session. Yeah. So people are still keep on joining. The morning, I think. So your classes might be started every day. On right? And every day it is same timings now. Okay. Yeah. So in the last class, we have seen the voltage regulation of alternator. We have started voltage regulation. Voltage regulation of alternator, it is a ratio of change in terminal voltage to the rated voltage. Change it, just a minute, I will switch on this light. Yeah. So the voltage regulation of an alternator, it is a ratio of change in terminal voltage to the rated voltage. Change in terminal voltage means E minus V is the change. From no load to full load, what is the change? It will be E minus V. But that is only magnitude difference. It's not vector difference. Magnitude difference to be taken. Okay? Yeah. That is required. Why to measure voltage regulation? The voltage regulation needs to be measured for various necessities, and it gives the information for the selection of insulation rating and for to design the AVR. It affects also the stability, parallel operation, etc. Okay, yeah. But voltage regulation of alternator is large compared with all other things. Voltage regulation of alternator is much more. If you compare with any other generator or any motor, alternators regulations are more. Why? Because armature reaction is more. Drop due to armature reaction is external. Yes, that is a majority. But when drop is more, regulation is more means, don't think efficiency is poor. Alternator efficiency is also good. Okay, if regulation is more means efficiency is not depends on the regulation. Regulation is different and efficiency is different. Regulation is only drop of voltage, but efficiency power loss. In our synchronous machine, armature reaction is major drop of voltage. It is causes major drop of voltage. But armature reaction does not cause any power loss. The armature reaction, it will not affect on the efficiency. Okay? Yeah. And we have seen the condition for zero regulation, condition for maximum regulation. Okay? Condition for zero regulation, cos theta plus phi is equal to minus Ia Zs divided by 2V. And that zero regulations can be obtained for the power factors which are closer to UPF. But maximum regulation is power factors closer to ZPF lagging. Okay. So based on that, we have drawn the curve, and also we have done some problems on the voltage regulation. And we have started the characteristics of alternator. We have completed OCC and ACC, open circuit characteristics and short circuit characteristic. Now let us continue the other characteristics, zero power factor characteristics. Okay. Zero power factor characteristics. ZPFC. Zero power factor characteristics. That is what? ZPFC. Zero power factor characteristics. ZPFC. And we know that. What is ZPFC? ZPFC is V versus IF. No? V versus IF. IA is equal to constant. Voltage versus IF. IA is equal to constant. And power factor is equal to ZPF lagging. Speed is constant. Speed is constant. Okay. V versus IF and a variation of terminal voltage with respect to field current. Current constant, other things are set to be constant. For that, see, the circuit diagram is, this is the load, RL load, pure inductive load, say. This is pure inductive load. Load is pure inductive load. It is variable load, variable inductive load. Variable inductive load. Yeah. The voltmeter. Here, speed is kept constant. N is constant. And this is IF, field current. IA has to be kept constant. This is terminal voltage V. Whereas this is pure inductive load. The pure inductive load. ZPF lagging load, na? Pure inductive load. That is ZPF lagging load. ZPF lagging load. Zero power factor, ZPF lagging load. And let us take IA constant here. IA is constant. Say some 20 amperes. IA, I want to maintain 20 amperes, say. Then measure the voltage. Measure the field current and voltage. IF and V. IF and V. Right? See. Are you ready? Yeah. Okay. Yeah. Dear students, are you ready? Yes, because just I'm seeing the students are still joining. Okay, but time is over already. Right. So let they will note down later. Yeah, it's almost over. All the students here. Fine. See, so this is pure inductive load. Pure inductive load means what is the power factor? ZPF lagging. Pure inductive load means power factor is ZPF lagging. Zero power factor lagging. If you take load is resistive load, say it will be UPF. Power factor is depends upon what? Load, type of load. So here we are taking ZPF lagging load, pure inductive load. This is alternator. This alternator. On this, we are measuring armature current and a variable inductive load is applied. So by varying the field current, we will note down the voltmeter reading. We will note down the voltmeter reading. And here, first point, when you are taking the first point, it will be kept at a minimum impedance position. first point will keep like this. First point is kept like that. I mean, see, all the loads are kept here. All the loads are first we are keeping here. So what is the meaning of that? Tell me. What is the meaning of that? That is nothing but short circuit. Hey, we are changing the load impedance. Impedance load we need to change. But impedance load means I will start from 0 onwards. We will keep on increases the load. And when if you keep this is at minimum impedance position, 0 position, all the phases are shorted. All the terminals are shorted, na? Yes, that is a short circuit test. It is nothing but simply short circuited. And for that, under short circuit condition, I will adjust the field current. I will adjust the field current such that the current will be 20 amperes. This is important. Current every time you need to maintain the 20 amperes. So for 20 amperes, say 2 amperes to be given. 2 amperes are given. When 2 amperes are given, we are getting 20 amperes. But what is the voltage? Voltage is 0. Voltmeter reading is 0. So current is 20 amperes, but field current is 2 amperes. What is the voltage? Voltage is 0. So this is nothing but first point is short circuit test. Short circuited, terminals are shorted. It is exactly short circuit test at rated condition. Yeah. Now, then we will increase the resistance. We will increase the impedance. Increase the impedance. When impedance is increased, what happened? Tell me. Current will reduce. When we are adding some impedance, current will reduce. Current will reduce less than 20 amperes. But to maintain the same current, what to do? You have to increase the field current. Increase the field current. Field current has to be increased. Say that is equal to some 3 amperes. 3 amperes. The 3 amperes means again current has increased to 20. Are you getting my point? When impedance increases, current reduces. IA is not 20. Current is reduced less than 20, say. But to maintain the 20 amperes, what to do? Increase the field current. And again, note down the reading. Note down the reading. So that is 3 amperes. 3 amperes, say this is some 50 volts. 50 volts. Voltage is not 0 now, because voltage across this impedance. Voltage across this impedance. Earlier they are short circuited, okay, voltage 0. But now voltmeter reading is not 0. It will show some value. Right? Yeah. Next, again, similarly, repeat the same procedure. Increase the impedance. Increase the impedance. When impedance is increased, current will again reduce. Current reduces. IA less than 20. But you need to maintain IA will be 20 always, because IA should be constant, no? Yes. So when impedance increases, current will reduce. But to maintain the same armature current, again increase the field current. Say that is equal to some 4 amperes. 4 amperes. And when you are applying 4 amperes, say this is some 80 volts. 80 volts. Like that. Take the readings. By taking the readings, a set of readings, then draw the graph. How it is going to be? The graph will be like this. This is the ZPFC. You draw the field current versus V. Field current versus V. The first point is the short circuit test. Na? First point is the short circuit test. Therefore, where the curve will start? Curve will start on the x-axis. Because here V is 0. Na? V is 0. This is corresponding to what? 2 amperes. For 2 amperes of field current, voltage is 0 here. V is 0. So curve will start from x-axis onwards. Curve start from x-axis. Because Y component is 0, voltage is 0. So for 2 amperes, voltage is 0. Now when field current increases, voltage increases. No? As impedance increases, we are increasing field current also to maintain the current rated. But when impedance increases, voltage drop across the impedance also more. So it is going to be like this. This is the ZPFC. Zero power factor characteristics. Zero power factor characteristics. Okay. ZPFC. And on ZPFC characteristics, zero power factor characteristics, E and V. In this, if you write the equation, E is equal to V plus IAZS, na? V plus IAZS or V0. If you write the equation for that, E at an angle 0. E is equal to V at an angle 0 plus IA. What is the current? IA is equal to minus 90 degrees and XS is equal to plus 90 degrees. Plus 90 degrees. Therefore, E is equal to V plus IA XS. It becomes V plus IA XS. Or just wait for some time to this equation. I'm going to explain there why unnecessarily it is. You may be getting confusing. So just have an idea about this is a ZPF. Zero power factor characteristics is it is similar to OCC. It is similar to OCC. If you draw the OCC, okay, be parallel to OCC. So ZPFC. This is the zero power factor characteristics. But only OCC will start from origin. ZPF start from some field current onwards. Okay. Yeah. This is zero power factor characteristics. Now, next characteristics are external load characteristics, load saturation characteristics. Next one is load saturation characteristics. Load saturation characteristics. Load saturation characteristics. Load saturation characteristics, they are V versus IF. They are V versus IF. IA constant, power factor is constant, and the speed also constant. Speed constant. V versus IA constant, power factor constant. See, these characteristics, and earlier we have drawn the characteristics, na? ZPFC, both are similar. Here also ZPFC also same, na? V versus IF. Here also V versus IF. IA constant, power factor constant. Power factor 0 also constant. When inductive load is there, if you use half load, full load also, its power factor ZPF lagging, that is also constant. The ZPFC and next characteristics, they both are same. Both are same. Otherwise, it is having its own importance. That's the reason we are discussing ZPFC separately. Otherwise, it will be same. No. Okay. This is inductive load, alternator, ammeter reading. Now I am using pure resistive load, say starting with resistive load. Resistive load. Also variable load. Okay. This is a voltmeter. IF, IA. And again, take the same readings. What is that? IA constant. IA is equal to constant. Say it is equal to some 20 amperes. Say 20 amperes. Say 20 amperes. Again, take the set of readings. This is IF and V. IF and V. Yeah. Circuit diagram is same. Only load has been replaced with the resistive load. Earlier I have used pure inductive load, na? But now I am using the pure resistive load. Resistive load I am using. Okay. Yeah. First point is same again. First point is same. It can be kept at 0 impedance position, 0 position, short circuit position. and increase the field current. Adjust the field current such that the current will be 20 amperes. The current is 20 amperes. Earlier also first point same, na? Even when I am using inductive load also, this point is same. But now here, earlier this is 2 amperes. For circulating 20 amperes for first point, short circuit test, IF is 2 amperes for 20 amperes. But now, even I am using resistive load, again I am short circuiting, then also field current is same, na? Then also field current IF is equal to 2 amperes to maintain the 20 amperes. Okay. Yeah. 20 amperes first point is same. First point for 20 amperes it may be inductive load, whatever may be the load, because we are not added the load at all. We are not added the load at all. So first point is same. That is the main key point. 2 amperes. When 2 amperes means voltage is 0. That's the first point is short circuit test is same. And we are also drawing current for same current, 20 amperes. Okay, yes. Now, then increase the load resistance. Increase the load resistance. When load resistance is increases, what is going to happen? Current reduces. Current reduce. But to maintain the same current, field current has to be increased. Are you getting? When load resistance increases, armature current decreases. But to maintain the same thing, again increase the field current. The field current may be some 3 amperes, like that. 3 amperes. It may be some 60 volts or 70 volts, like that. Okay? Yeah. It will be some 60 volts. Like that. Dash, dash, dash. You take a set of readings. And then draw the graph. Graph also same. Graph also same. IF and V is also same. This is load saturation characteristics for UPF, for unity power factor. For unity power factor. And similarly, draw for, this is for UPFC. If you draw for lagging power factors, 0.6 lagging, replace the load with 0.6 lagging. Simply remove the load with 0.6 lagging, then you are going to get the characteristics will be like this. This is 0.6 lagging, and this is 0.8 lagging. This is ZPF lagging, and this will be leading power factor. They will be this side. Leading power factors, ZPF leading. Okay. Yeah. So this is for UPF. See, this is for unity power factor. This is for 0.8 lagging. This is for 0.6 lagging. This is for ZPF lagging. For leading power factor, 0.8 leading, 0.6 leading, and ZPF leading. Zero power factor leading. Okay. Taken? Yes. And we are going to discuss very important discussion, impedance method, short circuit. After these characteristics, impedance, synchronous impedance method. Okay. Let us close this characteristics quickly. Here, unity power factor is there, na? If you take unity power factor reference, lagging power factor characteristics are right side they are shifting, leading power factor characteristics are shifting left side. You're getting lagging power factors are right side, leading power factors are left side they are shifting. Why reason? Reason is, see, reason is, for example, you want rated voltage, na? For example, if you want rated voltage, whenever if you want rated voltage, just a minute. This is 0.8 line. Yes. You want rated voltage in all the cases. See, this is V rated. Rated voltage. Rated voltage means if you want some 400 volts, say 400 volts. You want 400 volts. For unity power factor, this much of field current is required. This much of field current is required for UPF. But for lagging power factor, more field current is required. Na? Lagging power factor 0.8 lagging, say field current requirement is more. Why? Why? Because due to demagnetizing effect of armature reaction, voltage drop takes place. Voltage drop. But I need to maintain the voltage same. I want again 400 volts. 400 volts means field current. It requires more field current. More field current. Similarly, 0.6 lagging. For 0.6 lagging, drop is still more. Drop is more. So therefore, field current requirement will be still more. Again, ZPF lagging, totally demagnetization. So drop is more for ZPF lagging. The voltage regulation is maximum for almost ZPF lagging. So to maintain 400 volts for ZPF lagging means very large current is required. So alternator must be over-excited. Na? For lagging power factor, over-excited. When compared with UPF, it is more excitation is required. Whereas for leading power factor, if you take leading power factor, less field current is required. Field current has to be reduced, under-excited. So to maintain the same rated voltage, leading power factor's characters are shifting left side, lagging characters are shifting right side. Now on this, he has given in previous examination, GATE 2001 examination. Let me give the question. See, this is a GATE 2001 examination. The characteristics he has given, a group of characteristics, set of characteristics. E and V, this is IF. E and V, IF. So OCC is also another characteristics. These are the characteristics. This is UPF at IA rated. This is for UPF at IA rated. IA rated. Now this is OCC. This curve is OCC. This is A. This is B. This is C. And this is D. So the curve which represent for 0.8 leading power factor, at rated condition. 0.8 leading power factor rated condition is A bit. A bit is curve A, B bit, curve B, C bit, curve C, D bit, curve D. Tell me, what is your answer? Answer is C. Exactly. Answer is C. Okay. Can you tell me why not B? B also left side, na? B also left side. Why not B? Tell me. Why not B? Some of you tell me why not it is B? Just I want to know. Curve C correct only. Why not B? B also left side, na? B also left side. Rated current. Very good. Rated current. See, the characteristics, these group of characteristics, they are started from the same point. All they are started from the same point. Then only these are said to be related to rated current. Some 20 amperes means earlier we have drawn, na? The starting point is same. Why? Because short circuited, but current is equal to 20 amperes. I have drawn all the characteristics for 20 amperes. You have drawn all the characteristics for 20 amperes. So their first point, starting point must be same. That's the reason here also starting point will be here. So these are only set of characteristics. C, D, and he has given UPF at IA rated. Na? So therefore, C and D, they are related to rated condition. So this is UPF is given, which is left side, C. C is the left side. So C only characteristic. That is the correct. Fine? Yes. If it is given 0.8 lagging power factor, say, then I would have gone for D. Option D. Okay? Yes. And also another question in Telangana government, Telangana State Distribution Corporation Limited, TSDCL. The question is like this. The question is, yeah, here the field current to maintain rated terminal voltage, the field current to maintain rated voltage, the field current to maintain rated voltage is for A bit. ZPF lagging, the field current to maintain rated voltage is minimum for A bit ZPF lagging, B bit ZPF leading, okay. C bit is for pointer, C bit is UPF and D bit, equal for all. What is the answer? The field current to maintain rated voltage is minimum for A bit ZPF lagging, B bit ZPF leading, C bit UPF, D bit, equal for all. So what is your answer? Yeah. Your answer is B. ZPF leading. Correct? Minimum current is for what? ZPF leading. ZPF leading is minimum current. To maintain the, you want 400 volts, say, for ZPF leading, small current is enough. Because armature is magnetization. Armature flux aiding. Therefore, main field flux is not that much required. So field current is small is enough. Okay. So these type of questions that will be exist. Fine. Now, then coming to the next question, see. Not next question. Questions are like this only. Next characteristics. Compounding external load characteristics. External load characteristics. To draw the external load characteristics, alternator, load is connected, load current can be measured, this ammeter, the load. It's a voltmeter. Field current also can be measured. But first of all, what is the definition of external load characteristics? I have given already. External load characteristics is nothing but, that is V versus IA. IF is equal, other things are constant. Bro, load connected, what will be the constant? Tell me. IA changes, then how V changes? Okay, V versus IA means when IA changes, how V will changes. By keeping other things the same, other things are same. Other things means IF constant, Power factor constant. Power factor means load, same type of load. To draw the characteristics, entire throughout the characteristics, you have to use only same load, similar load, and resistive load only you have to take. Power factor constant and speed, anyhow, it will be constant. Speed is constant. Okay. V versus IA. V versus IA. See. This is IA. It will measure IA. This will measure V. This is IF. IF. But we need to keep IF is constant. IF will be kept constant. Speed is constant. N will be constant. N is constant. Right? Yeah. Now, then draw the characteristics. To draw the characteristics, this is IA and this is V. V. And take a set of readings. Take a set of reading. IF will be kept constant. IF is constant. Say some 10 amperes. 10 amperes, say. Then you need to note down IA and V. Armature current and terminal voltage. Armature current and terminal voltage. First, definition of the characteristics are important. Definition of the characteristics is important. Right. See, by looking at these characteristics, we will start from x-axis or y-axis. That is important. Where it will be started? X-axis or y-axis. From the characteristics, listen, I will give the field current some 10 amperes to say. Field current is given 10 amperes, that is constant. It is kept to constant. And we are rotating that machine. We are rotating that machine. Field current is given, we are rotating. It will cut the flux now. When field current is given, it is flux is there. EMF will be induced. Correct? Yes. It will be generated EMF, induced EMF. Okay. What about armature current? First, no load condition I will take. IA variable, na? IA means from 0 onwards we will take. No load condition. But under no load condition, field current is given 10 amperes rated value, speed is rated, then voltage is 0 or voltage, some voltage will be there. Some voltage will be there. Rated voltage will be there almost rated voltage. Say this is voltage is some 400 volts. This is 400 volts. 400 volts. Okay. Even IA is 0, voltage will be some 400 volts, say. Then where the curve will start? Because we have given field current, we are rotating. So it is cutting the flux, EMF is generated. The alternator under no load condition. No load condition. So when IA is 0, right? Voltage is equal to, this is voltage, V. I can say E is itself V, na? Yes. No load condition, E and V, both are same. No load condition, E and V. V is equal to E. Current 0. Let me take this as a reference. This as a reference. This is not characteristics. Just for reference I am taking. Now, increase the load. We are connecting the load. When load is connected, what happened? When load is connected, say, when load connected, current increases. Current increases. Current some 5 amperes, say. Current increases. But what happened? Voltage. Voltage will reduce or not? Definitely voltage will reduce. Voltage will reduce. It may be some 390 volts. Voltage will definitely reduce. Like that. Inductive load. For example, it is a resistive load. As load increases, current increases. As current increases, what will happen? Definitely voltage will reduce. And the leading power factor voltage increases. If you connect leading power factor, voltage increases. I am not changing any field current, dear students. I am not changing the field current. Field current is kept to constant. So no load condition 400. When load increases, voltage decreases. Voltage decreases to some 390 volts, say. If you want, you can maintain 400. How you can maintain? By increasing the field current. But I don't want to increase the field current. Field current is kept constant. Constant. Once adjusted, it is kept constant. So 400 volts, no load condition 10 amperes. we kept constant. And when load connected, load increases, voltage will be decreases for lagging power factor, and also resistive UPF also voltage decreases because voltage drop. Leading power factor, voltage will rise, rising of voltage. So based on that, the characteristics will be like this. These are the characteristics. See, this is for resistive load, and for inductive load, it is still more drop. This is for inductive load, and this is for 0.8 lagging load, 0.6 lagging load. This is UPF. Okay, 0.8 lagging. This is a 0.6 lagging. And ZPF lagging will be, this is ZPF lagging. The ZPF lagging. Similarly, leading power factor, rising, no? Leading power factor increases. 0.8 leading. ZPF leading. This is 0.8 leading, 0.6 leading, and this is ZPF leading. Okay. These are the characteristics. ZPF lagging and ZPF leading. Okay. But ZPF lagging is more drop. ZPF lagging is more drop. You can find ZPF lagging and ZPF leading both are linearly decreasing. For example, you see for ZPF lagging, if you take for ZPF lagging, E is equal to V0 plus IA. What is the current angle, power factor angle? Minus 90 into XS, say XS at an angle 90 degrees. What is that? V plus IA into XES. Therefore, E is equal to V plus IA into XES. E is equal to V plus IA into XES. But what is V? V is equal to E minus IA into XES. V minus IA into XES. This is dropping, drop, linearly decreases. Okay. Like Y is equal to, this is Y, say Y is equal to mx minus c. Y is equal to mx minus c. But this is c minus mx. Y is equal to, right, minus mx plus c. It is decreasing, na? Decreasing. Y is equal to minus mx plus c. Slope is negative, na? Slope is negative. The slope is negative. Negative slope. Decreasing. Y is equal to straight line, na? I think you are knowing straight line is not passing through origin. It is decreases. Similarly, if you take leading power factor, it will be rising. Same for lagging power. Leading power factor will be rises. Y component, what is the Y intercept? E is the induced EMF. No load condition. Okay. Yeah. Now, but for leading power factor, dear students, lagging power factor is decreases, UPF decreases, but whereas leading power factor voltage increases and also decreases. Because for leading power factor, what happened up to this period, up to this one, voltage regulation is negative. Voltage regulation is negative during this, in this. But here, what is the voltage regulation? Voltage regulation is zero. And from here onwards, what is the voltage regulation? From here onwards, voltage regulation is positive. Positive regulation. Voltage regulation is positive. Voltage regulation. That's the voltage regulation. That's the reason for leading power factor, it is increases and also it is decreases also. Negative regulation means voltage increases. Positive regulation, voltage decreases. But whereas for lagging power factor, voltage regulation always positive. That's the reason only drop of voltage. Okay. Now, the last characteristics, compounding characteristics. Last one, compounding characteristics. In your examination, how you want to test the questions for the students, he will give you a set of characteristics. Set of characteristics, sometimes you will find match the following, or sometime you may be given some characteristics you need to identify. Which of the following characteristics represent for some 0.8 lagging or UPF? So just to have an idea about these characteristics. Now last characteristic is compounding characteristics. Compounding characteristics are the IF versus IA. IF versus IA as V constant, power factor also constant, and speed is constant. Okay. For this, yeah. This is load. IF, the V. IA, but V should be constant, no? V should be constant. V is equal to 400 volts. That is required constant. That has to be maintained constant. That has to be maintained constant. This is IA, IF. IA and IF. Okay? Yeah. Yes. Yeah. I hope you understood the definition is important. Based on the definition, you can able to answer. This is IA. Fine. See, the main important thing here, you need to maintain voltage constant. Voltage is equal to 400 volts, say. That should be constant. That is our intention mainly. I want to maintain the voltage constant. In this way, you have to think. Okay. Tell me, first point. Listen, it will start from y-axis or x-axis. The curve will start from y or x-axis. It will start from, see, this is IF. We need to give variation of IS with respect to IA. And IA means compulsory, you need to start from 0 onwards. X-axis must be started from 0 onwards. When IA 0, no load condition, I want 400 volts. If you want 400 volts means compulsory some current must be given, na? Yes, some rated current nearly 10 amperes are given. When 10 amperes are given, we are getting 400 volts, for current is equal to 0. The voltage is 400, but field current must be some 10 amperes. 10 amperes. For what? 400 volts. IA is equal to 0. So this is the first point. First point, I am taking this as the reference. Okay? Yeah. Now, see, when later onwards, this is the first point, 400, I want 10 amperes. As load increases, what is going to be happen? As load increases, load connect to the load. When load connected, voltage decreases, no? This voltage decreases. But to maintain the same voltage, what we have to do? Field current has to be increased. I want to maintain 400 volts. As load increases, voltage decreases. But to maintain the same field current, for lagging power factor, drop of voltage. So field current has to increase to compensate drop. But leading power factor, as load increases, voltage increases. It is more than 400. Then what to do? Decrease the field current under excitation. So If you draw the characteristics, they are like this. For lag UPF also you need to increase. You need to increase for UPF. And lagging power factors also we have to increase. For lagging power factors we have to increase. The leading power factors, they are like this. This is for UPF, unity power factor. This is for 0.8 lagging. This is for 0.6 lagging. This is for ZPF lagging. And this is for 0.8 leading. This is for 0.6 leading. 0.6 leading. ZPF leading. Okay. These are just opposite to earlier characteristics. Earlier. You may raise a doubt. Sir, 0.8 leading, it is decreases, again increases, means as long as regulation is negative, I will decrease. But when regulation is positive, say leading power factor, positive, negative, 0. For leading power factor, it will be increases. When regulation is positive, say voltage decreases, na, again you have to increase. They are just opposite. Here you see, increases, it is decreases. As long as voltage increases, I will decrease the field current to maintain the same voltage. And when it is decreases, we will increase. Okay. So just write reverse. Fine. So this is about characteristics of alternators. Okay. Let's go through that. It is GATE examination is not that much is insisting on characteristics, but ESC examinations is asking. Other competitive examinations are there now. Mainly is focusing on the characteristics of alternators. Okay, other examination like state government examinations, right? Individual state government examinations will be there, no? Maharashtra Genco or TS Genco or AP Genco, DISCO. This type of examination is focusing. And we don't know even for GATE examinations also. Sometimes may be given, yes. Okay, right. Now, then let us start the another important topic, that is synchronous impedance method. Synchronous impedance method. Or voltage regulation method. First, before that, let us see voltage regulation methods. Voltage regulation methods. Voltage regulation methods. There are 4 methods of voltage regulation. Number 1, synchronous impedance method. Synchronous impedance method. Okay. Or EMF method is also called EMF method. EMF method. Second one is Rother's ampere turns method. Rother's ampere turns method. Ampere turns. The AD method. Rother's ampere turns method, or is also called MMF method. MMF method. And third one is zero power factor method. Zero power factor method. That is ZPF method. Zero power factor, ZPF method. ZPF method. Or it is also called Pottier method. Pottier method. Pottier method. The fourth one is ASA method. American Standard Association method. American Standard Association, the ASA method. American Standard Association method. These are the 4 voltage regulation methods. Okay, 4 regulation methods. First of all, why 4 regulation methods are required? Tell me. Only one method is there, then we would be happy. No, syllabus is less, and we can complete today itself regulation methods. No? But there are many voltage regulation because so they are not right. They are not developed simultaneously. They came one after the other. Synchronous impedance method, MMF method, they are not accurate. Synchronous impedance method will give the more than regulation, but MMF method give the voltage regulation less than the actual value. They are not giving correct results. So later onwards, ZPF method was developed. It is giving accurate results. And ASA method also, saturation is also taken into consideration. So anyhow, we are going to see one by one each and every point we are going to discuss. Okay? Yeah. But first of all, you want to measure voltage regulation. Direct method you can use. Directly you can measure. Apply the load, measure the full load voltage. Measure the full load voltage, 400 volts. Say. Remove the load. Same voltmeter measures the no load voltage. So you know no load voltage, full load voltage. Then regulation is equal to E minus V by V. Over. Na? Then why to do all these things? Directly never be measured voltage regulation. Because once you have designed your alternator, you want to test. So for example, 500 megawatt alternator. Can you provide 500 megawatt load in the laboratory? No. But different people also require different power factor. So some people require 0.8 lagging, some people require 0.6 lagging, some other require 0.8 leading, some may be UPF. Can you provide all varieties of loads in the laboratory? Not possible. Not possible. Okay. And that to be, if you do that experiment, direct loading 500 megawatt for 1 hour, it is experimented, say 500 megawatt hour power is wasted. Na? Yes. So that's the reason, never be direct methods. In the laboratory, these are the laboratory methods, indirect methods. Indirect methods, graphical methods. By drawing OCC and SCC, we can measure the regulation. But while you are conducting OCC, how much energy wasted? Only iron losses. Iron losses. And while you are conducting short circuit test, only copper losses. Mechanical loss, anyhow, it will be there. So once OCC, SCC, like characteristics have drawn, then you can leave the machine. You can leave the machine with that reading. You can calculate. All these are paperwork. Yes. Now you can calculate full load regulation, off load regulation, any power factor. All these are only just calculations. Okay. Indirect methods only can be done. So these are the indirect methods to measure the voltage regulation. Okay. Yeah. But among these important things, this is the 3-star method. This 3-star method. 3-star. Here 0 star, no star, nothing. This is single star, single star. This is also 0 star. In this voltage regulation methods, very important one is synchronous impedance method. Synchronous impedance method. Okay. Yeah, EMF method. So let us discuss that. And some students will ask, synchronous impedance method means, in this method we will measure synchronous impedance or EMF method. Rother's ampere turns. Rother's ampere turns means Rother's is the scientist who has developed this method. He has given Rother's MMF method. ZPF method or Pottier method. Pottier is also scientist. Pottier also scientist who has developed this method. Pottier method. Okay, Pottier is scientist. Rother's also scientist. But synchronous is not scientist. Dear student, synchronous impedance method means a synchronous is not scientist. So we are finding synchronous impedance. Let us discuss one by one. First, let me start with the synchronous impedance method. So in this class, we will complete the synchronous impedance method. See, synchronous impedance method. Synchronous impedance method. It is also called EMF method or EMF method. Okay, EMF method. In this method, why we are calling synchronous impedance method means In this method, we will measure the synchronous impedance. Synchronous impedance. And with the knowledge of synchronous impedance, excess is calculated, regulation is calculated. So since synchronous impedance is measured, that's the reason it is called synchronous impedance method. Okay. In this, ZS is measured. In this method, ZS is measured. ZS is measured by drawing OCC and SCC. By drawing OCC and SCC. After measuring ZS, then XS is calculated, XS is calculated. Thereby regulation can be calculated. Thereby regulation can be found. Regulation can be found. Since ZS is measured, that's the reason called synchronous impedance method. That's the reason called synchronous impedance method. So this is called synchronous impedance method because we are measuring the ZS. Synchronous impedance is measured. But why it is called EMF method? Why it is called EMF method? Why this is called EMF method? EMF method. Because in this we will use EMF phasors. Analysis can be done either by using EMF phasor or MMF phasor. Both can be done either by using EMF and MMF. See, EMF, E is proportional to what? E proportional to flux. Flux is proportional to field current. Field current is proportional to MMF, na? Yes, MMF. So that is FM, MMF vector. For example, it is FM, I can say M vector. Okay? This can be represented. The E can be represented with MMF vector also. Voltage can be represented with MMF vector. Proportional, na? Yes. MMF method. Or you can, if you want, you can represent voltage phasor or MMF phasor. This is EMF phasor. You can say EMF phasor, and this will be MMF phasor. They can be represented with anyone. In this, main important thing is, in this method, drop due to armature reaction, leakage reactance. Strictly speaking, drop due to armature reaction is flux phenomena. Drop due to armature reaction is flux phenomena. It can be represented with field current vector or MMF vector. And drop due to leakage reactance is EMF phenomena. Because due to leakage flux, self flux, an EMF is induced. It opposes the actual generated EMF. The leakage reactance drop means what? When current is going, flux links with this conductor and EMF is induced, statical induced EMF. That induced EMF opposes the actual generated EMF. Thereby net voltage decreases. So leakage reactance is EMF phenomena that can be represented with EMF vector. But in this method, total drop, entire drop is considered as drop due to, right, armature reaction. Entire drop is considered, or entire drop is represented with EMF phasor. Leakage reactance and armature reaction both are represented with EMF phasor. That's the reason this method is called EMF method. EMF phasors we are using. See, the reason is drop due to armature reaction. The drop due to armature reaction can be represented. Drop due to armature reaction is flux phenomena. Drop due to armature reaction is flux phenomena. And this can be represented, which can be represented with which can be represented with the field current vector, or MMF vector. MMF vector. Okay, yes. And a drop due to leakage reactance. Drop due to leakage reactance is EMF phenomenon. EMF phenomenon, which can be represented with EMF phasor, with EMF vector. EMF vector. But in this method, the entire drop is represented with EMF phasor only. Armature reaction also represented with EMF phasor. In this method, in this method, the entire drop is armature reaction drop also considered as EMF phasor. In this method, the drop due to armature reaction is also represented with EMF phasor. So therefore, total drop is represented with EMF phasor. That's the reason called EMF method. The EMF phasors we are using, everything is EMF phasors. That's the reason called EMF method. Okay, EMF method. Yeah. Anyhow, voltage can be represented with EMF. We are going to see EMF. The armature reaction, drop due to armature reaction, EAR say. EAR is equal to IA XA, I will show. EAL say, that is equal to IA into XL. They both are represented with EMF phasors. Voltage also, drop is equal to what? Drop is, units are volts, na? Yes, EMF phasors. Okay. See, this method requires OCC, and ZPFC. OCC and SCC, not ZPFC. OCC and SCC. OCC and SCC. So now let me draw the OCC, open circuit and short circuit characteristics. Okay. Second, draw the open circuit characteristics. Short circuit characteristics. Both I am drawing on the same graph. This is IF. This is E and ISC. Draw the OCC and SCC. Short circuit characteristics. This is OCC. This is SCC. Open circuit and short circuit characteristics. OCC, SCC. Draw the OCC and SCC. Okay. Again, Let us make it fast and we have to come to the questions mainly. Questions. OCC and ACC. With the knowledge of OCC and ACC, measure the synchronous impedance. After drawing OCC, ACC, measure the synchronous impedance. First step is draw OCC and ACC. Draw OCC, ACC. Next, measure synchronous impedance. Measure the synchronous impedance. Synchronous impedance ZS. And the ZS is equal to what? ZS is equal to open circuit voltage by short circuit current. OC voltage by short circuit current. But field current is same. Field current. Field current is the same both for open circuit voltage, both for OC voltage and AC current. Both for OC voltage and AC current. ZS, open circuit voltage by short circuit current. But field current must be same. Field current must be same. Right? Okay, based on this, open circuit voltage by short circuit current, we have drawn on the same graph. Dear students, x-axis is common, field current common. On y-axis, this is E and current. Two components we are drawing, open circuit voltage and short circuit current. Y-axis common for both voltage and current. Can I draw like that? Yes. 1 centimeter is equal to 10 volts, say. Or 1 centimeter is equal to 1 ampere. You can take any number of components. I can also take ZS also on that. ZS also, synchronous impedance also I am going to draw with respect to field current. So, yeah. So ZS, OC voltage by SC current. Now, if you draw that ZS on the graph, see. For example, this is 1 ampere. For 1 ampere of field current, I will measure. This is the open circuit voltage. This is the short circuit current. This is voltage. This is current. That is equal to ZS. See, this is the ZS. ZS. Similarly, for 2 amperes of field current, for 2 amperes of field current, this is 2 amperes. Say, this is open circuit voltage. This is short circuit current. That voltage by current is equal to, this is the ZS. This is a ZS. Like that, if you take for 3 amperes, 4 amperes, then your ZS will be like this. ZS is going to be, ZS is constant up to knee point, it is constant. ZS is constant up to here, but ZS will be decreases. From here onwards, ZS decreases. So ZS is constant up to knee point, ZS decreases. This is ZS or this is also XS. XS. So ZS is constant up to knee point. Up to knee point. Later onwards, it decreases. Here, thing is, why ZS is constant up to knee point? This is knee point. This is said to be called what? Knee point. Knee point. Up to there, ZS is constant. Why? Because both OCC and ACC, open circuit voltage by short circuit current, both voltage and current both are linearly increases. Both are linearly increases. Therefore, ZS is constant, no saturation. So, 2 straight lines, ratio of 2 straight lines is constant. But from knee point onwards, ZS is decreasing. Why ZS is decreasing? Due to saturation. ZS is decreases because OCC is not linear. ACC linear, but OCC not linear. The voltage is not that much increasing. Voltage increment is less compared with current. So, ZS is decreases. Why? Because increase in voltage is less. Open circuit voltage is not increasing that much. Slowly it is increases, but current is increasing fast. So therefore, numerator, denominator, dominate. Okay. So ZS is equal to EOC. Open circuit voltage means what? Open circuit voltage by ISC. Short circuit current. IF is the same. IF is same both for EOC and ISC. On that basis, we have drawn. So field current is same for voltage and current. Now, if you draw the ZS, that is going to be ZS. Okay. Yeah. So here important thing is ZS is not constant. Reason is ZS is not constant. What is the reason? Reason is, make a note. ZS is not constant. Reason is saturation. Reason is saturation. 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 And then we can call this part is said to be ZS unsaturated. This is said to be ZS unsaturated. But this portion is said to be ZS saturated. That is ZS unsaturated. No saturation up to constant, up to knee point. But later onwards it is ZS saturated. Saturated. Which is more, tell me? ZS unsaturated. ZS unsaturated is greater than the ZS saturated. Once it is saturated, say, pick value, reduce. Just keep in your mind. Yeah, fine. But in this method, where ZS can be measured, which value, which ZS you can take, saturated or unsaturated? For which field current can be taken? ZS, where ZS is not constant, ZS is varying, but which ZS to be taken is a matter. So, in this method, two concepts are there. We will take ZS corresponding to rated short circuit current. Rated current we will take, another one rated voltage also we will take. Rated current, rated voltage. So let us take both. In this method, ZS can be measured. ZS can be measured. ZS can be measured for the field current corresponding to. For the field current corresponding to. Field current corresponding to rated short circuit current. Rated short circuit current. Rated short circuit current. Then ZS by synchronous impedance method. ZS by synchronous impedance method is the EOC by ISC. EOC by ISC. IF EZ. IF EZ. ISC is equal to IA rated. IA rated. Field current. IF EZ. ISC is equal to IA rated. IF EZ. IA rated. Okay. Yeah. Rated field current. This is ISC is equal to IA rated. Field current corresponding to rated short circuit current. See. Coming back to that our diagram. This, you know your current, na? For example, this is our rated current, say. This is our rated current. ISC is equal to IA rated. ISC is equal to IA rated. Okay. ISC is equal to IA rated. For example, 20 amperes, you know, current is 20 amperes. For that current, what is the field current? For that, this is the field current. I am coming like this. I am coming to here. This is the field current. Field current. Once you know the field current, for the same 2 amperes, say field current, this is your EOC. This is your open circuit voltage. This is EOC. EOC. Now this EOC by ISC is equal to, this is the ZS. In this method, this is the ZS by synchronous impedance method. ZS synchronous impedance method. What is the ZS? ZS is also on the x-axis. ZS is also on the y-axis. I am drawing ZS. Variation of ZS with respect to field current. There is a ZS variation of ZS with respect to field current. Okay. So in this method, we are finding where you are finding ZS can be found. The ZS can be measured for the field current corresponding to rated short circuit current. So I know rated short circuit current, this is the field current. For the same field current, this is the voltage. This voltage by this current is equal to, this is the ZS. Okay, yes. So once that ZS is measured, rest of the things are only calculation. Rest of the things are calculations. Once ZS is known, next we will measure the XES. Next step is, after measuring ZS, calculate XES. After measuring XES, ZS, calculate XES. Calculate XES. XS is equal to what? ZS square minus RA square. RA will be given, RA known. XS is equal to ZS square minus RA square. Then calculate E. Calculate E. Once XS is measured, calculate E for E is equal to V cos phi plus IARA whole square plus V sin phi plus or minus IAXS whole square. IAXS whole square. Okay. I mean to say, this E can be calculated. Only in this method, ZS is measured, that's all. Once ZS is known, XS is calculated. After knowing XES, E can be calculated by using this relation. If you want to find regulation at half load, full load conditions, I will use full load current. Half load condition means half load current. You want 0.8 lagging or 0.6 lagging or leading power factor. For any required load condition, required power factor, E has to be calculated. Rest of the things are calculations only. Calculate E, then what is the regulation? Then regulation is equal to E minus V by V into 100. This is a regulation. Okay, E minus V by V into 100. The regulation methods, very simple. ZS is measured for IF is equal to IA rated. That IF is IA rated. Okay. But this method gives voltage regulation more than the actual value. This method gives the voltage regulation more than the actual value. This method gives voltage regulation. Gives the voltage regulation more than the actual value. More than the actual value. Actual regulation. Actual regulation. That's the reason called pessimistic method. That's the reason called pessimistic method. Pessimistic method. Pessimistic method means what? Bad method. Regulation is more means good or bad? Bad. It is bad. Bad method. Okay. Reason why? Why it is giving more regulation? What is the reason why it is giving more regulation? Voltage regulation. Let us see. Reason is reason. Reason is in this method we have measured ZS corresponding to rated short circuit current. So in this method what we have done, ZS is measured for the field current corresponding to rated short circuit current. Rated short circuit current. And we have measured related to ZS unsaturated portion. Unsaturated portion. So in this method, ZS is measured for the field current corresponding to rated short circuit current where field poles are active. Because under short circuit condition, armature reaction is purely demagnetization. Armature reaction is purely demagnetization. Therefore, there is no saturation. There is no saturation. So ZS is measured unsaturated portion. Once ZS is more means regulation also more, na? Yes. Once ZS is more, regulation also more. Regulation also more. ZS is not correct in this method, whatever you measure. ZS is more than the actual regulation. Strictly speaking, machine, we have taken short circuit condition. Field poles are active, but machine actually operate above knee point. Practical cases, it never operate below knee point. We have taken below knee point. Actually, the machine operate little above knee point. So therefore, this may be the actual ZS. We don't know. This may be the actual ZS. Actual ZS may be some other value. The actual ZS may be related to this portion. This may be the ZS actual, say. For example, this may be the ZS actual. This may be the ZS actual. ZS actual. But where we are taking, so ZS by this method is more. ZS by this method is more. Actually, machine works, actual working condition, field poles a little saturated. But we are taking for unsaturated portion. So ZS is more. When ZS is more means regulation is more. So the conclusions are like this. Listen. Reason is, in this method, right, the ZS is measured for the field current corresponding to rated short circuit current, which belongs to unsaturated portion. And the ZS is more than the actual ZS. That's the reason regulation is more. Because regulation is proportional to ZS, na? Yes, regulation is proportional to ZS. See, reason is, in this method, the ZS is measured. ZS is measured for the field current corresponding to rated short circuit current. Where the field poles are active. That is no saturation. Because demagnetizing effect of armature reaction. Okay, field poles are active. But under actual loaded condition, field poles little saturate. So ZS by this method is more than the actual ZS. ZS by this method is more than the actual ZS. But we know regulation is equal to what? E minus V by V into 100. That is equal to IA ZS divided by 100. V into 100. So regulation is proportional to ZS, na? Yes. Regulation is proportional to ZS. But ZS by synchronous impedance method is more than the ZS actual. ZS synchronous impedance is more than the ZS actual. Okay? Yes. And then regulation by synchronous impedance method. Is greater than the ZS actual. Okay? By this method, regulation is more. Why? Because saturation is not considered. dear students, practical cases saturation takes place, but in this method saturation is neglected. In other words, saturation is neglected. In other words, saturation is neglected. Saturation is neglected. Actually, saturation takes place, but due to short circuit, no saturation. Under short circuit condition, demagnetization, no saturation takes place. Okay. Yeah. Pessimistic is bad method. Regulation is more means bad. Pessimistic. Okay. And can I call this is the unsaturated synchronous impedance method? This is unsaturated. You have measured unsaturated portion. But modification of this method, that is said to be saturated synchronous impedance method. This is unsaturated, I can say. Next, saturated synchronous impedance method. There, what we are going to see, ZS is measured for the field current corresponding to rated open circuit voltage. Rated voltage. In this method, rated current we have taken, but saturated synchronous method, rated voltage will be taken. So let us see that one. So it is saturated synchronous impedance method. Saturated synchronous impedance method. Saturated synchronous impedance method. Here also same procedure, everything is same. Everything is same, but only measurement of ZS. IF. You see. Yeah, OCC and this is SCC. ZS will be same, na? ZS is same. ZS variation, ZS is same. Like this. This is a variation of ZS. Or that is nearly equal to XCS. Okay, nearly equal to XCS. ZS. See. After drawing OCC and SCC, ZS is measured for the field current corresponding to rated open circuit voltage. That is the main important thing. In this method, see, in this method, ZS is measured. ZS is measured for the field current. For the field current corresponding to rated open circuit voltage. Rated open circuit voltage. That means ZS saturated, or it is also called adjusted. ZS saturated or also called adjusted. That is equal to EOC by ISC. But IF is at EOC is equal to V rated. EOC is equal to V rated. EOC is equal to V rated. Earlier we have taken earlier what is that? IF is at IS is equal to IA rated. Are you getting the difference? IF is at EOC is equal to V rated. But earlier you see, earlier what is that? Earlier is IF is at IS is equal to IA rated. This is different. Here rated current reference, and next one is rated voltage is reference. EOC is equal to V rated. Okay. field current EOC is equal to V rated. See, this is a rated voltage. Say, this is a rated voltage. EOC is equal to V rated. EOC is equal to V rated. For this voltage, this is the field current. This is the field current. First, I know the voltage, and from here I will come to here, come down to the field current axis, and again, this is the current, corresponding current. This is the corresponding current, yes, ISC. This is corresponding current, ISC. Now this is corresponding ZS saturated. This is ZS saturated. ZS saturated. Okay. ZS saturated. Once you know the ZS, rest of the things are simply calculations only. ZS is measurement, that's all. Next, what do? Calculate XES. Once ZS is known, next step is calculate XES. But XS is equal to ZS square minus RA square. Next, calculate E. E is equal to what? Same relation. V cos phi plus IA RA whole square plus V sin phi plus or minus IA XS whole square. Then regulation. Regulation is equal to E minus V by V into 100. Regulation. Regulation is equal to E minus V by V into 100. That's all. Okay. But this will give a bit good result compared with earlier one. Okay. But this is also not giving accurate result. This is also more. Regulation is more than the actual regulation only. Why? Because we are taking OCC and SCC. SCC is taking SCC short circuit condition also is coming into picture. As long as short circuitation is there, demagnetization. This method also will not give accurate result. It is also giving more than actual regulation, but it is better compared with earlier one. Okay. Yeah. Fine. Now coming to the type of questions. What type of questions that can be asked on this? Will you ask all this procedure? No. But what are the questions? All questions are there already on the board. What is the questions you know? Let me read out the questions. ZS is not constant. Reason. ZS is not constant. Reason is saturation. Saturation is the region. Okay. OCC also linear. How you can get? Tell me. SCC linear. OCC also linear means ZS is going to be constant. ZS is constant. But OCC non-linear and voltage is not increasing much. Current is increasing faster. So denominator dominate. Magnitude decreases. That is saturation region. And also ZS unsaturated. ZS unsaturated A bit is more than the ZS saturated, less than the ZS saturated, equal to ZS saturated. It will be more. ZS unsaturated is more than the ZS saturated. This graph is, he has asked, 4 graphs are given. 4 graphs are given among this, which is variation of ZS with respect to IF. This is the graph is there. This is a ZS variation. ZS or XS variation. That is itself one question. ZS and XS. Okay. Now, let me give the important questions. Yeah. See, the questions are EOC is equal to V rated. EOC is equal to V rated. That IF is equal to 10 ampere. No. Let me take numericals itself. EOC is equal to some 400 volts. That IF is equal to 10 amperes. And ISC is equal to 20 amperes. That IF is equal to 5 amperes. Then ZS is A bit. ZS is 5 ohms, B bit, 10 ohms, C bit, 20 ohms, leave it. 40 ohms. 40 ohms. Yeah, tell me, what is the answer? EOC is equal to 400 volts. At IF is equal to 10 ampere. ISC is equal to 20 amperes. Then IF is 5 amperes. What is the ZS? How much ZS? So while you are calculating the ZS, both must be same field current. That is important. Both must be for same field current. Both must be same field current, na? Yes. But he has not given different values. That's the reason what to do. ISC is equal to, you have to calculate. For 10 amperes, you have to calculate. ISC is equal to 40 amperes. That IF is equal to 10 amperes. Correct? Yeah. SCC can be, linearity can be taken SCC, not for OCC. Not for OCC. Because SCC linear. 5 amperes, this is 20 means, definitely 10 amperes it will be 40. Current will be 40, na? 5 amperes 20 given. But I need to calculate both must be for same current, na? Both must be for same currents, for same things you have to take. Both must be for same values. Okay, this must be 10 ampere. This also must be 10 ampere. That is important. Therefore, then what is ZS? ZS is equal to EOC by ISC. EOC by ISC means it is 400 divided by IS is equal to how much? 20. Not 20, sorry. IS is equal to 40. 40. Then it is equal to 10 ohms. 10 ohms. That is correct. ZS is 10 ohms. Okay. And similarly, one examination, he has given question like this. Question is, EOC is equal to 200 volts. 200 volts at IF is equal to 10 amperes. 10 amperes. And ISC is equal to 20 amperes. At IF is equal to 5 amperes. 5 amperes. RA given, RA 3 ohms. 3 ohms. Then XS is, XS is A bit. 2 ohms, B bit. 3 ohms, C bit. 4 ohms, D bit. 5 ohms. 5 ohms. EOC 200 volts. ISC 20 amperes. RA given. Now you need to calculate what is the XS value. XS value. Okay. So again you have to take for 10 amperes, no? 10 amperes. ISC is equal to 40 amperes. At IF is equal to 10 amperes. So you need to take these two combination. These two combination to be taken. Okay. Because current must be equal, na? Current must be same. 10 ampere, 10 ampere. So then ZS is equal to how much? EOC by ISC. EOC by ISC. EOC is 200. IS is 40 amperes. 5 ohms. ZS 5 ohms means what is XS? XS is equal to ZS square minus RA square. RA square. That is 5 square minus 3 square. Is equal to how much? It is 4. 4 ohms. XS is 4 ohms is the answer. XS is 4. 4 ohms. So these are the simple questions. Yeah. Now, let me give one gate question. Okay. Previous gate question, gate 2009, he has given the question is, EOC is equal to 2000 volts. 2000 volts. IS is equal to 400 amperes. This is also IF is equal to 20 amperes. This is also IF is equal to 20 amperes. 20 amperes. Field current. Okay. Then the Then the drop in synchronous impedance. Drop in synchronous impedance. Synchronous impedance at rated armature current. At rated armature current of 200 amperes. 200 amperes is A bit. 0 volts, B bit. 10 volts, C bit. 100 volts, D bit. 1000 volts. 1000 volts. 1000 volts. EOC is equal to 2000 volts at field current 20 amperes. IS is equal to 400 amperes at field current of 20 amperes. Then the drop in synchronous impedance at rated armature current is how much drop? Drop. What is the answer? 1000 volts. Very good. 1000. Why? Because see here, the solution is both are given for same current, na? Same field current, same excitation. Therefore, no conversions are required. Directly you can take ZS is equal to EOC by ISC. ISC. That is 2000 divided by 400. That is equal to 5 ohms. 5 ohms. Then drop in synchronous impedance is equal to IA into ZS. IA is equal to 200 amperes he has given, and 5 ohms is equal to 1000 volts. The 1000 volts. Okay, 1000 volts. That is a simple question. Now, then another gate question. See, GATE 2014 examination. One question. Let me give. GATE 2014. That is also for 2 marks. Of course, this is also for 2 marks. The question is like this. Question is an alternator, a 3-phase, a 3-phase, 400 volts alternator, star connected, 3-phase 400 volts star connected alternator. Star connected alternator gave the following test results. Gave the following test results. The OC test. OC test. EOC is equal to 400 volts. 400 volts. Line to line. Line to line. At IF is equal to 2.3 amperes. Line to line, let me write clearly. Line to line. At IF is equal to 2.3 amperes. 2.3 amperes. But SC test is given. SC test is ISC is equal to 10 amperes. 10 amperes. Okay. RMS value, phase value, RMS phase value. This is given phase value. Phase value at IF is equal to 1.5 amperes. 1.5 amperes. Okay. Then the synchronous impedance. Then the per phase synchronous impedance. Then the per phase synchronous impedance. Synchronous impedance at rated voltage. At rated voltage. Rated voltage is dash. At rated voltage is dash. This is a question. At rated voltage is dash. Okay. Question is clear, na? Yes. A 3-phase 400 volts star connected alternator gave the following test results. OC test is EOC 400 volts, line to line voltage. At IF is equal to 2.3 amperes. SC test is ISC is equal to 10 ampere RMS value. Of course, if nothing is mentioned, AC component will be always RMS values only. But both are not given for same field current. And you need to find synchronous impedance at rated voltage. Rated voltage means for 2.3 amperes you have to find. So, see, IS is equal to, ISC is equal to how much? 10 amperes. At IF is equal to 1.5 amperes. Given, this is given. But you need to find out ISC is equal to, at IF is equal to, at IF, for IF is equal to 1.5 amperes, your ISC is equal to 10 amperes. But at IF is equal to 2.3 amperes, what should be the ISC? What should be the ISC? ISC is equal to 10 into 2.3 by 1.5. How much tell me? To calculate it. Let me see that my calculations I will be having. But you also tell me what is that values. That value is equal to 15.33, correct? 15.33 ohms, 15.33 amperes. Then ZS is equal to, now we need to calculate ZS is equal to what? ZS is EOC by ISC at IF is at EOC is equal to V rated. Is asked EOC is equal to V rated. And that is IF is equal to what value? 2.3 amperes you need to find. Therefore, ZS is equal to how much? Per phase. It is per phase means line voltage is given. 400 means line. That is equal to 400 divided by root 3 divided by 15.33 is equal to how much? That is equal to 15.06 ohms. 15.06 ohms. Okay? Yeah. 15.06. Right? Now, lastly, let us do. The only thing is you have to find for which field current. Both must be for same field current. Of course, he is asking for rated voltage means rated voltage 2.3. So calculate short circuit current also for 2.3. Then take the ratio. Last question. Yeah. The question is GATE 2007 examination. This is also for 2 marks. The question is a 3-phase 25 kVA 400 volts 25 kVA 400 volts delta connected armature. Very important problem. Delta connected alternator. It's not star connected. Delta alternator gave the following test results. Gave the following test results. Give the following test results. OC test. OC test is EOC is equal to, EOC is how much given? EOC is equal to 360 volts. 360 volts. At IF is equal to 2.5 amperes. 2.5 amperes. Similarly, SC test. SC test is ISC is equal to IA rated is given. ISC is equal to IA rated. IF is equal to 2.5 amperes. Both are given for same current. IF is equal to 2.5. Okay. Neglect RA. Neglect RA. Armature resistance can be neglected. Then the voltage regulation. The percentage voltage regulation. The percentage voltage regulation at percentage voltage regulation at rated condition for 0.8 leading power factor is dash. Fill in the blanks question is dash. The percentage regulation at rated condition for 0.8 leading power factor is dash. Question is clear now? Okay. So IS is equal to IA rated. Then you calculate here. Since delta connection, no, it is delta connection. Therefore, line voltage is equal to phase voltage. Is equal to how much? 400 volts. The data given, it is always line voltage. Line phase both are same. Both are same. 400 volts. Then IL is equal to kVA divided by root 3 into VL. Root 3 into VL. So that is equal to, what is the kVA? 25 kVA is given. Divided by root 3 into VL. VL is 400. 400. Therefore, what is the current? The current is equal to 36.08. 36.08. But what is the phase current? That is a line current. We need to calculate always phase current is equal to 36.08 divided by root 3. Root 3. Since it is delta connection, na? Delta connection root 3. That is equal to 20.83. 20.83 amperes phase current. Okay. Now calculate the ZS first. ZS. But ZS for which value you need to calculate? ZS can be calculated from the test results only. Test results. This is voltage and this is the current. IS is equal to IA rated. IA rated means what is the current? Tell me. This current is equal to 20.83. 20.83 phase value only you have to take. And some students will raise a doubt. This 360 volts is line voltage or phase voltage? Not given line or phase, but so phase line both are same. Phase line both are same means it is 360 volts is line same, phase same. Current, but both will be normally we need to take per phase values. Okay. Yeah. Now, so lastly, just 1 minute I am going to close. So you need to calculate ZS. What will be the ZS value? Tell me. So therefore, ZS is equal to EOC by ISC. Both are given for same field current. That's the reason nothing to worry. That is 360 divided by 20.83. 20.83 is equal to how much? ZS value? That is equal to 17.28 ohms. 17.28 ohms per phase value. Per phase. Okay. Now, then calculate E value. E. E is equal to square root of V cos phi plus IA RA whole square plus V sin phi minus IA XS whole square. Why? Because it is leading, na? Minus IA XS whole square. So that is equal to V. V. But which V to be taken? Tell me. Can you take 360 volts or 400? 400. While you are finding regulation, rated voltage only you have to take. Test results may be different. OC test results 360 volts is given. Okay. Short circuit, open circuit, you can do for any value. But while calculating, it must be rated value. It is 400 into cos phi how much? 0.8 leading. This is 0. IA is equal to IA, some current you are getting now. Yes. IA is equal to how much? IA is equal to 20.83. But that is 0. Whole square. V sin phi 400 into 0.6 minus IA 20.83 into XS we are calculated now. XS is equal to how much? XS is equal to 17 point. Earlier we have calculated XS value. XS is equal to 17 point. 17.28 whole square. Okay. This value is equal to how much you are getting? 341 volts. 341 volts. Then regulation is equal to E minus V by V into 100. E is equal to 341 minus V how much? 400 divided by 400 into 100. that is equal to minus 14.56%. Okay. Minus 14.56%. This is your answer. Right? But there is a choice of doing mistake. Where you will do the mistake? Where you are calculating ZS, EOC by ISC, but don't take 400 volts. You need to take only whatever the data given. OC test, SC test results only to be taken to calculate ZS. But while you are substituting in this equation, you have to substitute the rated value as given. Rated voltage anyhow always rated value only need to be taken. Very big mistake what the student will do. 400 volts is taken. First V phase voltage is equal to 400 by root 3 they will take. There your problem will be ends. That's all. You have taken delta connection, you are missing, say your total answers are going to be wrong. Correct? Delta is given means per phase current is equal to IL by root 3 we have taken delta. Phase voltage, line voltage is same. Yeah. Now, so I can stop here. I think we will be having next class. So with this, the synchronous impedance method is completed. Okay, one question also given in GATE 2020, good question that we will see. But time is over now. Okay. So you can leave the class. Fine. Anybody is having doubts, you can stay or else you can leave. We'll be having again class at 9 o'clock now. 9 from onward signals will start. Okay. Yeah, I think chart is not enabled. Chart is not enabled. I don't know. Next class is for everyone. I don't know. EOC line or phase. Always EOC you be taken as phase value, say. Phase values. Graph will be taken always. Graphs will be always for phase values. Will be always for phase values only. I told yesterday that is. When you are drawing, always pair voltage. One doubt is, sir, is it was star connected? Then the given voltage is always line voltage only you have to take. In the data given, always you take line voltage only. Line voltage. Line voltage. Always you need to take line voltage. Delta connection kabatti line phase both are same. Okay. The value of current when field current is not equal. When field current is not equal means you have to bring that to voltage. Voltage is known now. To that voltage you have to bring. Voltage you have to bring. Okay. You want previous slides? Huh? Yes, you can see. Okay. I think now I think the chart. Why I don't know. I think chart is not enabled. Okay, anyhow, we will see in the next class. Any doubts are there? If any doubts are there, you can please chart. Question 9. Hand raise is option is not giving. I think it is not coming. I don't know why. What happened? Okay. Hand raising. Right. Hand raising. Yeah, it is there. Now, anyone is there? Hand raising. Yes, I am unmuting. If you want, you can ask your doubts. Hello, I am unmuting.
Sir?
Yes, hello. Tell me.
Sir, IF value, different value. How is calculated? Please repeat, sir.
IF is different values are given. We need to take for only rated voltage. You bring rated voltage. For example, tell me what is that EOC? EOC is equal to some 400 volts. Say.
Yes, sir.
Here in the earlier question, your doubt is?
Yes, sir. First question.
Huh?
First question. Previously, sir.
Okay, this first question. Yes.
Yes.
When 400 volts 10 amperes are given, current is given for 5 amperes. But
Yes,
you have
sir.
to bring current to the voltage. ISC is linear. OCC not linear. I don't know. If it is voltage is given, IF is equal to 10 ampere 400. I am not sure that 5 amperes it is 200 volts.
Yes.
But current can be taken for any value. So always current you can shift, not voltage. Short circuit current can be taken. Short circuit current 5 amperes are there, you can bring that into 10 amperes.
Okay, sir.
Conversely is not correct. Don't bring. EOC is equal to 400, IF 10 amperes. For 5 amperes, it is EOC 200. I am not sure. It is non-linear. If saturation neglected, you are correct. Saturation neglected, you will be correct. Okay.
Okay.
So you bring that to voltage. Voltage, that is better. Yeah. Next, anyone? Hello?
Hello.
Hello? Yeah, tell me.
Hello, sir.
Yeah.
Sir, can you explain the last question once?
This one,
Yes, sir.
Where is your doubt?
Sir, that you said that delta connected, sir.
Delta connected. Okay. This one. This one.
Yes, sir. Yeah.
Delta connected, unless otherwise given, you take always, it will be line voltages. In this data given, always line voltages. This is total kVA. Okay.
Yes.
But OC test results, he has given EOC is equal to 360. He has not given for 400. Can be given anything. But both are given for same field currents. This is also 2.5. This is also 2.5.
Yes, sir.
Therefore, I can calculate ZS is equal to 360 by IS is equal to IA rated given.
Yes, sir.
But is this 360 phase voltage or line voltage? For example, say line voltage. Line also equal to phase voltage. That's the reason is not writing here particularly. If it is given line or phasor, it both are same. Line or phase both are same. That's the reason he has not given. You can take line also same answer, phasor, because phase line both are equal. Okay. This is only doubt or anywhere?
Sir, in the solution, the next step, sir.
Solution? Here,
sorry.
here you have to take V 400 volts.
Okay.
Why?
Sir,
test results are different. On the nameplate details, it will be 400 volts. On the data given, a 3-phase 225 kVA, 400 volts. That there you have to take.
But sir, that 0.6 you have taken here, sine phi. 0.6.
Here leading, 0.8 lagging, 0.8 leading power factor. Sine phi is equal to 0.6 only. Cos phi 0.8. That's the reason sine phi I am taking. V sine phi.
But sir, that 0.6, how not getting?
Cos phi is equal to how much? Cos phi is given 0.8, leading is given. You need to find out regulation for 0.8 leading.
Yes,
Cos phi point means what is the phi? That's 6.86 degrees. Then sin phi is equal to how much?
0.6.
0.6. That's why. 36.6.
Got it, sir.
Okay, right.
Sir, sir, you said as in compounding characteristic that as load increases, the voltage decreases, and for the leading power factor, if load increases, voltage increases. Then, sir, for the lagging power factor, then if load increases, then what will happen to the voltage?
Where?
For lagging power factor in compounding characteristics.
Compounding characteristics. Here, na? Okay.
Yes, sir. Sir, as you said, if leading power factor, if load increases, then voltage also increases.
Yes. That's the reason we need to decrease the field current.
Yes, sir. Then for what, if what lagging power factor then?
Lagging power factor voltage you drop only. There is no question. Drop means you have to increase the field current. They are increasing the field current. This is increasing field current. increasing, keep on increases.
Okay. But what happened to the voltage, sir?
Voltage decreases, drop. No, sorry. You need to maintain the voltage constant. Voltage constant means drop can be composite. How you can bring again to 400 volts? Field current has to be increased. That is what we are doing.
Okay, means if load increases, voltage also increase in lagging power factor.
Huh, which one? Lagging or leading?
For lagging.
Lagging power factor, as load increases, voltage decreases. This is 400. Right now you are getting 400. For example, say this is 400. 400 volts. I need to maintain constant. But when load increases, inductive load, voltage will reduce. This is 380 volts, say 380. Again, I want to increase the voltage to 400. What to do? Field current has to be increased.
Yes, sir.
That is what we are doing. Field current is increased. Okay.
Yes, sir.
Right.
Sir, one general doubt is there, sir. Sir, if a plant is having generating capacity of 16.5 volt, megawatt, and kilowatt, 16.5 kilowatt, and we are stepping it up to the 220 kilowatt. Then, sir, with the help of the step up. But instead of stepping it with the help of the step up transformer, why we can't generate this up to 220?
That is highly difficult. The generating station, you want to generate that much voltage means, first of all, speed must be very high, and insulation, will it withstand insulation? And how many number of turns are required? The size of the machine increases, rotor size increases, that all the limitations. Turbine is capable of running or not, all the things.
Okay, sir, means we have to design all the machines in that manner,
Yes.
that capacity.
Yes. Availability. Remaining things also will be taken into consideration. Okay.
Okay. Thank you, sir.
Right. Hello, anyone? Hello? I'm unmuting. Okay, tell me. Okay, so I will
Hello,
start the session.
Hello, sir.
Hello.
Sir, in this compound characteristics, sir, sir, the leading characteristics I have not get, sir. For leading power factor.
Leading power factor regulation, positive, negative also, na? First,
Yes.
I have understood this one.
Yes, sir. This understood, sir.
But this is means here as load increases, voltage, as long as it is a regulation negative, it is increases, and regulation may be zero also. Regulation positive, it is decreases. But I want to maintain always 400 volts means what to do? As long as voltage increases, we need to decrease the field current. Reversal of that. Next characteristic, whatever I have drawn, it is just opposite to this. Okay? As load regulation negative means what? Voltage increases. But you need to maintain voltage, what to do? Field current has to be decreased. Field current, we are decreasing the field current.
Okay, sir.
When regulation is positive, say, positive means voltage decreases, then field current need to be increased. Right?
Okay.
Yeah.
Yes.
Yeah. Okay. So I'm closing the session and then we will meet in the next class. Right.